in this lecture, we are going to talk about binary operations. Now, what is a binary operation? A binary operation is a function that, given two entries from maybe some set A, produces some elements in another set B. So, for example, if we have one set, maybe A here, B, then we have another set here, which is A operation B. The binary operation is the function that takes us from this set, which is AB, to this other set, which is A operation B. So, for example, let's say we have a certain set A here, collection of numbers, for example, 1, 3, and 5. And then we have another set here, which is 1, 9, and 25. See that the binary operation is what would take us from this set A to this other set B. Now, you can all see that 1 squared is 1. Then 3 squared is 9. And then 5 squared is 25. So, under this operation, we can see that the operation asterisk is defined as the squares of each of the members of A. And that will lead us to the elements of B. For example, let's assume we have another collection in a certain set, 3, 4, 5. And then we also have another collection, the members here, 12, 19, and 28. You see that if we square 3, we will get 9. And if we add 3 to 8, 9 plus 3 is 12. If we square 4, you get 16. 16 plus 3 is 19. If we square 5, it's 25. 25 plus 3 is 28. So the operation is x squared plus 3. That is how this binary operation is defined in this case. So, for example, a binary operation is defined by A operation B equals A squared minus B squared plus AB, where A and B are real numbers. You are supposed to evaluate root 2 operation 3. So, what will be the result of root 2 operation 3 under this binary operation? Now, A operation B equals A squared minus B squared plus AB. So we are going to evaluate root 2 operation root 3. Now, this root 2 is A and root 3 is B. So wherever we see A, we'll put root 2. And wherever we see B, we'll put root 3. So this becomes root 2 squared minus root 3 squared plus root 2 times root 3. And root 2 squared is 2 minus root 3 squared is 3 plus root 2 times root 3 is root 6. So this is equal to 2 minus 3 is minus 1 plus root 6. And when we rearrange, we'll get root 6 minus 1. So we have, given that M operation P equals M squared plus P squared minus MP, evaluate for operation 3. So M operation P equals M squared plus P squared minus MP. So what will be for operation 3? So just as the example we did, M represents 4 represents M, and then 3 represents P. So wherever we see M, we'll put in 4, and wherever we see P, we'll put in 3. So this becomes 4 squared plus 3 squared minus 4 times 3. 4 squared is 16 plus 3 squared is 9 minus 4 times 3 is 12. 16 plus 9 minus 12 equals 13. There are 3 major operations under binary operations. The first is commutative, the second is associative, and the third is distributive. When we say a binary operation is commutative, what does it mean? It means that, for example, if you perform A operation B, it is the same as B operation A. In other words, the order doesn't matter. If you change the order of the operation, you will get the same result as the first. What about associative? For example, A operation B operation C is the same as A operation B operation C. So this is how the rule of the associative goes. And then the distributive is, for example, if we have A operation B operation C, the distributive says we can perform A operation B in one bracket, and then we use it to perform another operation against A operation C in another bracket. So we have this question: which of the following binary operations is not commutative? So it says that A operation B is A plus B minus AB. Now, we'll take each and then we'll find, remember, for a binary operation to be commutative, A operation B must be equal to B operation A. So now it says that A operation B equals A plus B minus AB. What is B operation A? It's equal to B plus A minus BA. If we arrange, it's going to be A plus B minus AB, which is the same as the first. So therefore, A is commutative. Let's come to B. A operation B equals 2A plus 2B minus AB. What is B operation A? It's 2B plus 2A minus BA. If we rearrange, we will get 2A plus 2B minus AB. It is also the same as the first, and that makes B also commutative. So this is commutative, and B is also commutative. Let's come to C. A operation B equals 1 over A plus 1 over B. What is B operation A? It's equal to 1 over B plus 1 over A. If we rearrange, we'll get 1 over A plus 1 over B. It's also the same as what we started with. So C is also commutative. So by default, the right answer is D. But why is D correct? A operation B equals A minus B plus AB. Now let's find B operation A. It's equal to B minus A plus BA. If we rearrange, it becomes minus A plus B plus AB. So you see that AB and AB are the same. Then here is minus B, but here we have plus B, so they are different. And here is plus A, but here we have minus A, which are also different. So A operation B is not equal to B operation A. And that is why D is the correct answer. A binary operation is defined on a set of real numbers by x operation y equals x plus y plus 6, where x, y, z are all real numbers. Now, the first part is we are supposed to calculate minus 3 operation 5 operation 2. And then the second part, we are supposed to determine whether or not the operation is alpha commutative and then beta associative. So let's start with the I portion. Minus 3 operation 5 operation 2. But remember that the operation is x operation y equals x plus y plus 6. So in order to solve this, we need to first determine 5 operation 2, the bracket first. So 5 operation 2 equals, wherever we see x, we put 5, and wherever we see y, we put 2. So it becomes 5 plus 2 plus 6. 5 plus 2 is 7. 7 plus 6 is 13. Then, having gotten the result of 5 operation 2, which is 13, in the next step, we will then take minus 3 and do minus 3 operation 13. So this means that wherever we see x, we put in minus 3, and wherever we see y, we put in 13. So this becomes minus 3 plus 13 plus 6. 13 plus 6 is 19. 19 minus 3 will give you 16. The second part of the question, we need to determine whether the operation is associative. So for associative, A operation into bracket B operation C is the same as A operation B operation C. So let's first do this part. What is A operation into bracket B operation C? So we need to first find B operation C. And that is equal to, wherever we see x, we put in B, and wherever we see y, we put in C. This becomes B plus C plus 6. Now, having gotten this result, we then do A operation B operation C. This means that wherever we see x, we put in A, and wherever we see y, we put in B plus 6 plus 6. So A operation B operation C equals A plus B plus C plus 6 plus 6. And this is equal to A plus B plus C plus 12. So this is the result for A operation into bracket B operation C. Now let's do this. A operation B in one bracket operation C. So we need to first determine A operation B. And this is equal to, wherever we see x, we put A, and wherever we see y, we put B. a plus b plus 6. Then now let's do a operation b operation c. So wherever we see x, we put a plus b plus 6. And wherever we see y, we put c. So this becomes a plus b plus 6 plus c plus 6. And this is equal to a plus b plus c plus 12. So we can see that a operation into bracket b operation c equals a plus b plus c plus 12. And then a operation b in one bracket operation c is also a plus b plus c plus 12. And therefore, since a operation b operation c is equal to a operation into bracket b operation c, then the binary operation is associative. Binary operation is defined by p operation q equals p squared plus q squared minus pq on the set of real numbers. A, determine whether or not the operation is commutative. And B, evaluate minus 2 operation 7. So the operation is p operation q equals p squared plus q squared minus pq. So in commutativity, a operation b equals b operation a. So what is a operation b? It's equal to a squared plus b squared minus ab. Then what is b operation a? It's equal to b squared plus a squared minus ba. When we rearrange, we'll get a squared plus b squared minus ab. So since a operation b is equal to b operation a, then the binary operation is commutative. Now the second aspect is saying we should evaluate minus 2 operation 7. So this means that wherever we see p, we put minus q. And wherever we see p, we put minus 2. And wherever we see q, we put 7. So minus 2 operation 7 equals minus 2 squared plus 7 squared minus into bracket minus 2 times 7. Minus 2 squared is 4 plus 7 squared is 49 minus into bracket minus 14. So this becomes 4 plus 49 plus 14. 4 plus 49 is 53. 53 plus 14. 53 plus 14. The final answer is 67. A binary operation, asterisk and delta, are defined on the set of real numbers by a operation b equals 2a plus ab and x delta y equals x plus y minus xy, where a, b, x, y are all real numbers. The a portion is determine whether or not the operation delta is commutative, and the b portion is we should evaluate in one bracket 3 operation 2, which is 3 asterisk 2 delta, in another bracket 5 delta 3. So we are supposed to determine that whether or not this part of the operation is commutative. So that is x operation y equals x plus y minus xy. So let's determine y operation x. This is equal to y plus x minus yx. So if we rearrange, we'll get x plus y minus xy. So since x operation y equals y operation x, then the operation delta is commutative. Now we are supposed to evaluate in one bracket 3 operation 2 operation, in another bracket 5 operation 3. So the first thing we need to do is to determine 3 operation 2. But remember that comes under the asterisk, which is a operation b. So we know that a operation b equals 2a plus ab. So this is equal to, wherever we see a, we put 3, and wherever we see b, we put 2. So 2 times 3 plus 3 times 2. And 2 times 3 is 6 plus 3 times 2 is 6, which is equal to 12. Now let's also find 5 operation 2, 3. Now we know that x operation y equals x plus y minus xy. So 5 operation 3, wherever we see x, we put 5, and wherever we see y, we put 3. Becomes 5 plus 3 minus 5 times 3. So 5 plus 3 is 8 minus 5 times 3 is 15. And this gives us minus 7. So at the end of the day, in one bracket, 3 operation 2 operation 5 operation 3 will be equal to 12 operation minus 7. So we need to find 12 operation minus 7. We need to find 12 operation minus 7. And that is equal to 12 plus minus 7 minus, in one bracket, 12 times minus 7. So this becomes 12 minus 7 plus 84. So the final answer becomes 89. Under binary operations, there's something known as identity element. For example, 1 plus 0 equals 1. 2 plus 0 equals 2. 13 plus 0 is 13. 1000 plus 0 equals 1000. So we see that it doesn't matter any real number that we choose. If we add it to 0, we'll get back that same number. Now let's come here. 1 times a equals a. 1 times 3000 equals 3000. So it doesn't matter the number that we multiply 1 by, we'll get back that same number. So under addition, 0 plus any real number does not change the results. We get back that same real number. And then 1 times any real number will give us that same real number. So this means that under addition, 0 is the identity element. And under multiplication, 1 is the identity element of real numbers. So the identity element is an element such that a binary operation performed on it and any other given element, the result is the given element. So, for example, the identity element is normally represented by E. So, A operation E equals A. This is the identity element. A binary operation is defined on the set of real numbers by x operation y equals x plus y minus 2, where x, y are members of real numbers. Find the identity element. So the binary operation is x operation y equals x plus y minus 2. So remember what we said. A number, for example, A operation, the identity element will give us A. So let's find A operation, the identity element under this operation. So this means that wherever we see x, we put A, and wherever we see y, we put the identity element E. So A operation E equals A plus E minus 2. But we said that the identity element, anytime we use it on an operation, we should get back the original number. So A operation E equals A. This implies that A plus E minus 2 equals A. So let's look for E. E equals A minus A plus 2. A minus A is 0. So this means that E equals 2. And therefore, the identity element under this operation is 2. So the binary operation is defined on a set of rational numbers by A operation B equals 2AB. Find the identity element. Now, remember that we said that A operation, the identity element equals A. The operation is A operation B equals 2AB. So we need to find A operation E and equate it to A. So A operation E equals 2AE. Then we'll equate this result to A. So 2AE equals A. We can now find the identity element E equals A over 2A. So A and A cancels and E equals 1 over 2. Now that we've been able to find the identity element, the next thing is to be able to find the inverse of a binary operation. So what the formula says is that A operation A inverse equals the identity element. So anytime you operate a number, an operation by its inverse, you will get the identity element. A binary operation is defined on a set of real numbers by A operation B equals half AB. Find the inverse of 2 under the operation. So we are supposed to find A inverse. But we know that A operation A inverse equals the identity element. So the first question we need to ask ourselves is, what is the identity element under this operation? We don't know yet. So the first task will be to find the identity element of the operation. But we know that A operation, the identity element is A. So let's find A operation, the identity element. And A operation E equals half AE. Then we will then take half AE and equate it to A, since A operation E equals A. So this implies that half AE equals A. Then let's make E the subject. E equals 2A over A. This implies that E equals 2. So the identity element is 2 under the operation. Now that we found the identity element to be 2, then we can then use this formula to get A inverse. So let's find A operation A inverse. This is equal to 1 over 2A A inverse. Then we have to equate it to the identity element. But the identity element is 2. And therefore, half A inverse equals 2. So we multiply both sides of the equations by 2. So these 2 and these 2 cancel. So A inverse equals 4. So A inverse equals 4 over A. A binary operation is defined on the set of real numbers by A operation B equals A plus B plus 3 over 4, where A, B are all members of the real numbers. Find I, the identity element of the operation. I, the inverse of a real number x, and I, the inverse of 2 over 5. So A operation B equals A plus B plus 3 over 4. What is the identity element? We know that A operation, the identity element is A. So we need to find A operation E. A operation E equals A plus E plus 3 over 4. Then we have to equate all of this to A. So A plus E plus 3 over 4 equals A. So this A and A can go away. And final answer, E equals minus 3 over 4. But remember, the second part of the question, they're asking us to find the inverse of the number x. So we know that A operation A inverse equals the identity element. And we know that the operation is A operation B equals A plus B plus 3 over 4. So A operation A inverse equals A plus A inverse plus 3 over 4. So we'll then take this and equate it to minus 3 over 4. So A plus A inverse plus 3 over 4 equals minus 3 over 4. So we can make A inverse the subject and take everything to the right hand side of the equation. This becomes minus 3 over 4 minus 3 over 4 minus A. So this is equal to minus 3 over 2 minus A. So in factorizing minus out, A inverse equals minus into bracket A plus 3 over 2. Then the last part of the question is, what is the inverse of 2 over 5? In other words, A equals 2 over 5. So we'll then put 2 over 5 into this equation. So A inverse is equal to minus into bracket 2 divided by 5 plus 3 divided by 2. So we can find the LCM 10. 10 divided by 5 is 2. 2 times 2 is 4 plus. Here's 5. 5 times 3 is 15. But there is a minus here. So this is equal to minus 4 plus 5 is 19. 19 over 10. A binary operation is defined on the set of real numbers by x operation y equals x squared minus 2xy plus y squared, where x and y are all real numbers. A. we should find m such that 2 operation minus 5 equals root m. And b, we should simplify in one bracket n plus 1 operation n divided by n where n is not equal to 0. So let's start with the a part. The binary operation is x operation y equals x squared minus 2xy plus y squared. So what will be 2 operation minus 5? It's equal to, wherever we see x, we put 2, and wherever we see y, we put minus 5. So this is 2 squared minus 2 times minus 5 plus minus 5 squared. This is equal to 2 squared is 4. Then minus 2 times 2 is minus 4. Minus 4 times minus 5 becomes plus 20. Then plus minus 5 squared is 25. And this is equal to 49. 20 plus 25 is 45 plus 4 will give us 49. But he says that 2 operation minus 5 equals root m. So we'll then take this result and equate it to root m and find m. So this implies that root m equals 49. So we square both sides of the equations and find m. So m equals 49 squared is equal to 2,401. That is the value of m. Then the b portion of the question says that we should simplify n plus 1 operation n divided by n. So this means that, so simplify n plus 1 operation n divided by n. So wherever we see x, we put n plus 1, and wherever we see y, we put n. So this is equal to n plus 1 squared minus 2 times n plus 1 times n plus y squared, which is n squared, divided by n. This is equal to n plus 1 squared is n squared plus 2n plus 1, then minus 2 times n plus 1 times n becomes minus 2n squared, then minus 2n plus n squared all over n. This is equal to, see that n squared plus n squared is 2n squared minus 2n squared will give us 0. So we are left with 2n minus 2n. That will also give us 0. So the final answer is left with 1 over n. But n is not equal to 0. The binary operation is defined on the set of real numbers by x operation y equals root x plus y for all x and y which are real numbers, where x is greater or equal to 0. The first task is to evaluate 3 operation 2 times 3 operation 4. And the second task is we should find n such that n operation 5 equals 7. And then the third aspect is we should determine whether or not the operation is commutative. So let's come to the first aspect. Let's evaluate 3 operation 2 times 3 operation 4. So what we must first do is to evaluate 3 operation 2, and that is equal to root 3 plus 2. Then the next aspect is to evaluate 3 operation 4, and 3 operation 4 will be equal to root 3 plus 4. So now, having found 3 operation 2 as root 3 plus 2 and 3 operation 4 as root 3 plus 4, we'll then go ahead and multiply. So this implies that 3 operation 2 times 3 operation 4 equals, in one bracket, root 3 plus 2 times the other bracket, root 3 plus 4. This is equal to root 3 times root 3 is 3 plus 4 times root 3 is 4 root 3 plus 2 times root 3 is 2 root 3 and 2 times 4 is 8. And 3 plus 8 is 11 plus 4 root 3 plus 2 root 3 is 6 root 3. So the final answer becomes 11 plus 6 root 3. Then the second part is in which you find n, such that n operation 5 equals 7. So let's find n operation 5. This is equal to root n plus 5. Then he says that we should n operation 5 equals 7. This means that root n plus 5 equals 7. So root n equals 7 minus 5. Root n equals 7 minus 5 is 2. We can then square both sides to remove the square root, and therefore n equals 4. Then the last aspect is we are supposed to determine whether or not the operation is commutative. But remember that he said x operation y equals root x plus y. So our job is to find y operation x, and that is equal to root y plus x. So in rearranging, it becomes x plus root y. We can see that x operation y is not equal to y operation x, and therefore this binary operation is not commutative. The operation delta defined on the set of real numbers R is P operation Q equals PQ over 4 plus P plus Q, where P and Q are real numbers. Find the inverse of Q. Okay, so what we will do is that we know the formula that Q operation Q inverse equals the identity element. But in the question, we are not given the identity element. So the first task will be to find the identity element. But we know that Q operation, the identity element equals Q. So let's find Q operation, the identity element. Q operation E equals QE over 4 plus Q plus E. We'll then take this result and equate it to Q. So QE over 4 plus Q plus E equals Q. So we'll then find E. Now let's multiply through by 4. If we multiply through by 4, this 4 will go away. So it becomes QE plus 4Q plus 4E equals 4Q. You can see that this 4Q and 4Q can go away. And therefore, we are left with QE plus 4E equals 0. So we can factorize E out. Q plus 4 equals 0. The only way this equation can be 0 is when E equals 0. And therefore, the identity element E is equal to 0. So having found the identity element, we can then go ahead to find the inverse of Q. So Q, operation Q inverse, what will be the result? It's the same as Q inverse divided by 4 plus Q inverse. This is equal to, so now we found Q operation Q inverse. So we then take that result and equate it to the identity element, which is 0. So Q inverse over 4 plus Q inverse equals 0. So from here, we'll then find Q inverse. So we'll multiply through by 4. So we'll get Q inverse plus 4Q plus 4Q inverse equals 0. So we'll make Q inverse the subject. Q inverse plus 4Q inverse equals minus 4Q. So we factorize Q inverse out. So Q inverse, in one bracket we have Q plus 4 equals minus 4Q. So Q inverse is equal to minus 4Q divided by Q plus 4 as a final answer. A binary operation is defined on the set of real numbers by x operation y equals x plus y plus 10. Find the identity element. And B, we should find the inverse of 3 and minus 5 under the operation. So what is the identity element? The operation is x operation y equals x plus y plus 10. Okay, so we know that A operation, the identity element equals A. So let's find A operation E. It's equal to A plus E plus 10. We then take A plus E plus 10 equated to A. So A plus E plus 10 equals A. Now let's make E the subject. So E plus 10 equals A minus A. So E is equal to minus 10. So the identity element is minus 10. Now let's then find A inverse. What is the inverse of A? We know that A operation A inverse equals the identity element. So let's find A operation A inverse. This is equal to A plus A inverse plus 10. Then now we then take this result and equate it to minus 10. So this implies that A plus A inverse plus 10 equals minus 10. So let's make A inverse the subject. Equals minus 10 minus 10 minus A. So A inverse equals minus into bracket 20 plus A. So that is the value for A inverse. Now that we have the value for A inverse, we can then go ahead and find the inverse of 3 and minus 5. So what is the inverse of 3? The inverse of 3 means that we should just put A equals 3. So that is A inverse equals minus 20 plus 3. And that is equal to minus 23. Then for minus 5, we then put A equals minus 5. So A inverse equals minus into bracket 20 minus 5. And this is equal to minus 15. So the inverse of 3 and minus 5 under the operation is minus 23 and minus 15 respectively. A binary operation is defined on the set T equals, the set of T is 2, 3, 4, and 5 by A operation B equals 3A plus 2B minus AB. The first part is we should copy and complete the table below. And the second part is we should show whether or not T is closed under the operation. And the third aspect is we should evaluate in one bracket 3 operation 4, operation 3, operation 5. So now the operation is A operation B equals 3A plus 2B minus AB. So now let's copy and complete the table. So we need to find 3 operation 2. So 3 operation 2, what will we get? To be 3 times 3 plus 2 times 2 minus 3 times 2. And what will we get if we do that? We'll get 7. So that means that this part is 7. Then this part is 3 operation 4. 3 operation 4 equals 3 times 3 plus 2 times 4 minus 3 times 4. The result is 5. So this side is 5. Then we come here, 4 operation 2. 4 operation 2 equals 3 times 4 plus 2 times 2 minus 3 times 4. The result you get is 8. And therefore this aspect is 8. If you do 4 operation 3, you will get 6. And therefore we are done with our table. We've completed filling our table. Now, the B part is saying we should show whether or not T is closed under the operation. Now, the T is closed if all the members that we have here are all members of the set T. So if we find any member here which is not part of the set T, then T is not closed. You see that when we look through, we only have the members of T are 2, 3, 4, and 5. So if we look here, we have 2, 3, 4, and then 5. But these are the only members of T. The rest, we have 6, we have 7, we have 8, we have 9. So these members which are 6, 7, 8, and 9 are the elements that does not make T closed, and therefore the operation is not closed. This is not a closed operation. Now, we are supposed to simplify 3 operation 4, operation 3, operation 5. So the first task, let's find 3 operation 4. 3 operation 4, what will we get? 3 operation 4 is 5. And then let's also find 3 operation 5. 3 operation 5, the answer is 4. So the next task then is to find 5 operation 4. 5 operation 4, and the answer is 3. So 3 operation 4 is 5, and then 3 operation 5 is 4. So the next step is to find 5 operation 4. So 5 operation 4 is 3. So therefore 3 operation 4, operation 3, operation 5 equals 3. So this is equal to 3. A binary operation is defined on the set of real numbers by A operation B equals A plus B over root AB. Evaluate minus 1 operation minus 2. So A operation B equals A plus B over A root AB. So what is minus 1 operation minus 2? So wherever we see A, we put minus 1, and wherever we see B, we put minus 2. So this becomes minus 1 minus 2 over square root of, into bracket, minus 1 times minus 2. This is equal to minus 1 minus 2 is minus 3 divided by minus 1 times minus 2 is minus square root of 2. So the answer becomes 3 minus 3 over root 2. But we don't have that in our answer. So all we then need to do is to rationalize. Rationalize by multiplying both the numerator and the denominator by root 2 over root 2. So this becomes minus 3 root 2 over root 2 times root 2 is 2. So the final answer becomes minus 3 root 2 over 2. Minus 3 root 2 over 2. So the correct answer is D. A binary operation is defined on the set of real numbers by A operation B equals, in one bracket, root A plus root B. In another bracket, root A minus root B. Find the value of x if x operation 2 equals 1. So the operation is A operation B equals, in one bracket, root A plus root B. In the other bracket, root A minus root B. So what is x operation 2? This is equal to root x in one bracket plus root 2 in the other bracket. Then in the second bracket, we have root x minus root 2. So we see that this is just difference of 2 squares. So it becomes root x times root x, which is x. Then plus root 2 times minus root 2 becomes minus 2. But we know that x operation 2 is equal to 1. So we then take x minus 2 and equate it to 1. And therefore x is equal to 1 plus 2. And x is equal to 3. So a binary operation is defined on a set of real numbers by x operation y equals 5x over 1 minus 3y, where x, y are all real numbers, for which real number is the operation undefined. So x operation y equals 5x over 1 minus 3y. For which real number is this operation undefined? This operation is undefined if and only if 1 minus 3y is equal to 0. So we can make y the subject. So 3y is equal to 1. Y is equal to 1 over 3. The only instance in which this operation is undefined is when y is equal to 1 over 3. So answer D is the correct answer. A binary operation is defined on the set of real numbers by x operation y equals x squared minus y squared plus xy, where x, y, and are all real numbers. Evaluate root 3 operation root 2. So x operation y equals x squared minus y squared plus xy. What is root 3 operation root 2? This is equal to root 3 squared minus root 2 squared plus root 3 times root 2. Root 3 squared is 3 minus root 2 squared is 2 plus root 3 times root 2 is root 6. So this is equal to 1 plus root 6 as the final answer. So a binary operation is defined on a set of real numbers by A operation B equals A over B plus B over A. If in one bracket root x plus 1 operation, in another bracket root x minus 1 is equal to 4, find the value of x. So we need to first find root x plus 1 operation to another bracket root x minus 1. So that is equal to root x plus 1 over root x minus 1 plus root x minus 1 over root x plus 1. So from here we can find the LCM, which is root x minus 1 in one bracket, root x plus 1 in another bracket. So this side becomes root x plus 1, and this one and this cancels. Root x plus 1 plus another bracket root x minus 1, and this cancels. We are left with root x minus 1. This is equal to root x times root x is x plus root x times 1 is root x plus root x times 1 is root x plus 1 times 1 is 1 plus root x times root x is x. Root x times minus 1 is minus root x minus 1 times root x is minus root x minus 1 times minus 1 is plus 1 divided by this becomes difference of two squares. Now becomes root x times root x is x minus 1 times 1 is 1 minus 1. So this becomes this plus root x minus root x can go. And so we are left with 1 plus 1 plus x plus x. So we are left with 2x plus 2 divided by x minus 1. And then the question is saying that this is supposed to be equal to 4. So we will then take this answer and equate it to 4. So 2x plus 2 divided by x minus 1 equals 4. So we multiply both sides by x minus 1. When we do that, we will be left with 2x plus 2 equals 4 times x minus 1. We then expand 2x plus 2 equals 4x minus 4. Then we group like terms. We bring 2x here and we take 4x there. So 4x minus 2x equals 2 plus 4. 4x minus 2x is 2x equals 2 plus 4 is 6. Divide both sides by 2. And then x is equal to 3. So x equal to 3 is the final result. A binary operation is defined on R, the set of real numbers, by x operation y equals x plus y minus 3xy for all xy, which are real numbers. For what value of x is the inverse non-existent? So the binary operation is x operation y equals x plus y minus 3xy. Now, in order to find the inverse, what we need to do is to find the identity element. But we know that A operation, the identity element is A. So let's do A operation E. This is equal to A plus E minus 3 A E, or that's X here, is equal to A. So this A and this A can go away. So 3AE is equal to minus E is equal to 0. So you can factorize E out. We are left with 3A minus 1 equals 0. The only way this can be 0 is when E is equal to 0. So the identity element E is 0. Then we'll then come and do A operation A inverse is equal to the identity element. So what is A operation A inverse? It is A plus A inverse minus 3A A inverse is equal to the identity element, which is 0. So we can then group like terms. A inverse minus 3A A inverse equals minus A. We've taken this to the other side of the equation. So we can factorize A inverse out. We are left with 1 minus 3A, which is equal to minus A. So A inverse is equal to minus A over 1 minus 3A. That is the value of A inverse. Now, for what value of A will the inverse be non-existent? This will happen if and only if 1 minus 3A is equal to 0. So 3A is equal to 1 and A is equal to 1 over 3. So the answer is 1 over 3.